Hello there, and today we're going to have a look at SI units, standard form, and prefixes in the context of physics. So you might be shocked to know that there are only 7 SI base units, and SI there stands for Le Système International de Unités, or however you say it, my French isn't the greatest. Essentially, it's the international system of units, and those definitions have been scientifically agreed upon by the scientific community. Now, a base unit has a very specific physical definition that has been internationally agreed upon. For example, I'm going to give one away. The kilogram used to be based off of an actual mass that they had in Paris. So that particular mass was 1 kilogram, exactly 1 kilogram. It was the definition of kilogram. It has since been updated, so it doesn't match that kilogram. You can look it up there. The definitions are quite cool. You don't need to know them, but they are quite cool. All other SI units that we use are called SI derived units, and they have a definition in terms of a combination of these base units. Now, there are only 7 base units. I'd like you to take a moment, pause the video, see if you could think of the 7 and what you think they might be. I've obviously already given one away. So write down the unit, so like kilogram, the symbol, little k, little g, and what it measures, mass. And if you take a look at what it measures, it might give you a little bit more of a hint as to the other things that you need. Good luck. So hopefully you got these 3, second, meter, and kilogram, measuring time, length, and mass. The other 4 are a little tricky. The next one I have on my list relates back to temperature. And sorry if you use degrees Celsius, but our SI unit for temperature is Kelvin. We do not use degrees Celsius. The next one relates back to electricity, and it might not be the one that you think it is. And to me, it's actually not the more fundamental one. And that is ampere. Everything else inside electricity can be based off of our base units, including amperes there. The next one you probably had to think of chemistry to get, and that's a mole, or the amount of substance. And the last one, I'll be highly impressed if anyone got. It measures luminosity, or sort of like brightness, how bright something is. And it's a candela. It relates back to the times when we used to talk about having a standard candle for how bright things are. So stars used to be measured in sort of standard candles, how many standard candles you'd need to make the same brightness as a star, which I think is a little bit ridiculous. We don't tend to use candela anymore. We tend to use other sort of measurements that are based off the other SI units, and it's sort of agreed among the scientific community or the astronomy community that those are the units they're going to use. Now, some of you are thinking, well, I've got Newton and joule and watt, and we studied those at GCSE, and they were definitely allowed as proper answers. And those are derived SI units. So in some instances, we use these accepted units that are defined as a combination of SI base units. So 1 Newton isn't, related back to the weight of an apple. 1 Newton is defined as a combination of those 7 SI base units. And to find that definition, to find that unit combination, we just use an equation and substitute the units in. So if we wanted to see what 1 Newton is equal to, we take an equation that's got the units of newtons in it, such as force equals mass times acceleration. And we simply substitute the units in. So instead of force, we write the units that force is measured in, newtons. Instead of mass, we write the units that mass is measured in, kilograms. And instead of acceleration, we write in the units that acceleration is measured in, meters per second squared. So a Newton is defined as a kilogram meter per second squared. Now, oftentimes, especially at A level, when we start to write our units and we have units inside denominators, we use negative exponents instead. It makes it a lot clearer with regards to what we mean by that slash, because sometimes if you've got, say, specific heat capacity, where you've got units of joules per Kelvin per kilogram, This looks kind of weird, and some people might go, well, is this kilogram part of this denominator, or is it separate? Or so if you just go joules per Kelvin per kilogram, it's very, very clear that both of those things are actually in the denominator. So I'd like you to pause the video and try to find the SI base unit combination for a joule. So trying to find the SI base unit combination for a joule, you might say, well, there's loads of formulas that involve energy. You can pick any of them. So E equals mgh is usually my go-to. E equals a half mv squared is another one that's really good for this. And then you just plug your units into your equation. So instead of energy, we've got joules. Instead of mass, we've got kilograms. Instead of g, or the acceleration due to gravity, we've got meters per second squared. And instead of height, we've got meters. And then we write that in the form that's a little bit easier to understand. So those 2 meters end up going together to make a meters squared. And rather than a per second squared written with a slash, we write it with a negative exponent. So we get 1 joule is a kilogram meters squared per second squared. Now that's the actual definition of a joule. If you were to ask someone, what is 1 joule? They would say it's 1 kilogram meters squared per second squared. And then if you were to ask a scientist, what is 1 kilogram? They could go look up the definition. It's not the mass anymore, but it's something like that. And your exam likes to use these sort of little bits as multiple choice questions because it shows that you know your units and you understand how the units go together. But it doesn't always just put them in base units. Sometimes it combines the derived units. So I'd like you to pause the video now and try to find out what a joule is in terms of a Newton. So previously we found that a joule is a kilogram meter squared per second squared and a Newton is a kilogram meter per second squared. Now we could combine these algebraically, which is just we've got 2 equations and we're trying to put them together. So we can take the definition for a joule and take out that kilogram meter per second squared, which is equivalent to our Newton, and then substitute those in and we get a joule is a Newton meter. Alternatively, we could just pick another equation. We pick an equation that's got joules in it, or some type of energy, and newtons in it, or some type of force. Any equation with an energy and a force will work, such as work, or energy, is equal to force times the distance. Plugging in our units, work done is measured in joules, force is measured in newtons, and distance is measured in meters. So we get joule equals newtons times meter. So as I've said before, multiple choice lends itself very well to asking these types of questions. So I'm going to give you a few multiple choice questions. I'd like you to pause the video, give it a try, and then we'll go through the answer. So the first question's up there. Pause the video, give it a try. Alright, so the question says, the units of physical quantities can be expressed in terms of the fundamental base units of the SI system. In which line in the table are the fundamental units correctly matched to the physical quantity? So charge, which is Q in equations, we need to come up with an equation that's got charge in it. So current is charge per unit time, which means charge is current times time. Now, if we substitute our units in there, charge is measured in I is amperes and T is seconds. So an ampere times a second. So this one is not correct. Now power, we've got power is energy per unit time, but notice that that energy isn't a SI unit, or SI base unit rather. So we might want to come up with the energy one first. So energy is like a half mv squared. And so energy is going to be a half, well that doesn't have any units. Mass is in kilograms and V is in meters per second, but that's squared, giving us kilograms meters squared per second squared, which as a side note, we could see D can't be correct because it's got the wrong exponent on our seconds. But now we can actually use that inside our expression for power. And so power is a kilogram meters squared per second squared all over a second, or a kilogram meters squared per second cubed, which is good. So our answer is B. Now, just to be thorough, let's show that that's not the correct one for potential difference. Now again, you can use this from any equation, but we might as well use it from the definition of voltage, which is energy per unit charge. And we already saw that energy is a kilogram meter squared per second squared, and a charge is amperes times seconds. So our potential difference is then going to be a kilogram meter squared per second cubed per ampere. And so we've got the kilogram, we've got the meter squared, but we're missing the second to the -3 per ampere. So that one's not correct. And our answer definitely is B. All right, give the video a pause and give this one a try. So it asks, which of the following is not a unit of power? Now, when they ask you these questions, it's almost like a true and false. I would recommend that you write like a T and an F next to each question so that you know which ones are true and which ones are false. But the big thing with that is then you don't fall into the habit of going, yes, I know a watt is the unit of power. I'll tick C as correct. And then actually you get that incorrect because you haven't read the question. So I would highly recommend that you just write a little true and false, and then you could go back and double check. Yep, it did ask for not, so it is asking for a false. So we should straight away be able to see that watts are a unit of power. We should know that one. And then to get to further ones, we use our equation. So power is energy per unit time. So power is measured in, or watt is equal to, a joule per second, which would be written as joule per second. So straight away, actually, we could say that B is false because it's got the wrong exponent on that S. It needs a -1 there. That being said, we're just going to go through the other ones so that you can see how the other ones are true. So we'll try to find out where joule is, so we can link that to any sort of energy equation, mgh, a half mv squared, and we get that a joule is a kilogram meter per second squared times meter, or to write that out properly, a kilogram meter squared per second squared. And if we plug that into our expression for watts, we get kilogram meter squared per second squared times seconds to the -1, or a kilogram meter squared seconds to the -3. That makes D true. And now A, we could find our definition of a Newton and plug it in and da-da-da-da, or we could be a bit savvy and look and go, right, I need something that links power, and Newton is a measure of force. I need something that links power and force. And if you look through the data sheet, you will find an equation that is P equals FV, which you haven't dealt with at GCSE, but I just want to show you that equations work for units, and you don't need to know how the equation works. As long as you know that the equation works, it'll work for units. It doesn't, I mean, like this equation here does have some stipulations on it, but that's okay because the units need to work. So a watt is, force is measured in newtons, speed is measured in meters per second, or if we write it with our superscript notation, newtons meter per second. True. So our final answer there should be B, and we could always double check. We've got a true, false, false, sorry, a true, false, true, true. So this one is the odd one out, so the answer is B. Third question for you here. Give the video a pause and give that one a try. So we've got which is equivalent to the ohm. And if you notice, all of those answers have got a joule in there, which means it's linking ohms, or resistance, to joules, or energy. So we want an equation that has energy and resistance in it. The other thing that we should notice is that there's no volts inside there. There are coulombs, but there's no volts. So we want to stay away from having voltage in our equation. So we might want to use, so rather than like a V equals IR type thing, we might want to use something like P equals I squared R, because then power is energy per unit time. And that gives us our resistance and our energy inside the same equation. Now, I has got units of amperes, And we don't have any amperes in there either, so we probably want to put the definition of current into there so that we can get some charge. So we've got energy per unit time is equal to charge per unit time squared times resistance, expanding that out. We can get rid of a factor of t in our denominator and then rearrange our equation for R. From here, we can substitute our units in. So R, or ohms, resistance, is equal to energy, joules, times time, seconds, over charge, coulombs, and that is squared. Or if we rewrite this as one line, we've got joule seconds per coulomb squared, which is B there. Having something like this as a multiple choice question is quite common, and that being said, they are quite tricky. So there is a list of 20 multiple choice questions. The first one is very tricky, but you can do it based off units. And the other 19 are sort of similar to these three. These three questions are actually in there. Not all of the answers are B. I don't know why the three that I picked are all B. But do give those a try. The mark scheme is included at the bottom on the Firefly page. And keep in mind, they are tricky. So scale is the next thing that we're going to talk about. And you need to keep scale in consideration when you're dealing with physics. You're expected to know roughly what types of distances and dimensions are consistent with the calculations you're completing. If you end up with a current of 1,000 amps for going through your charger, you should be able to go, nah, that's not sensible. You know, my plug probably has a 3 or a 5 or an 11, maybe a 13 amp fuse in it. You know, it's not sensible to be over that number. And physics is a little bit odd in that sense because it's a science that doesn't really focus on a specific scale, which is completely different from what you get in the other, like, big three for science. In chemistry, mostly you focus on the scale of atoms. Chemists are interested in how electrons interact with each other and how the atoms interact with each other to form molecules. And as such, the scale of their experiments tends to be like atomic to microscopic range. In biology, we're more interested in the molecules and how the molecules go together in that macrochemistry, which happens inside living bodies, whether it's a plant or an animal or a different classification. And it means that they look at molecule-sized interactions up to sort of like the size of a cell. But in physics, we've got all of the extremes. We look at particle physics, which is ranges of femtometers, significantly smaller than sort of like the chemist range of atoms to molecules. We look at, you know, macro objects, sort of like your forces and your pulleys and systems like that, all the way up to astronomy, where we've got ranges of light years, and even that isn't a very big unit for what we're dealing with. And if you want to see just how vast that scale is, this channel, it can be a YouTube if your Adobe Flash isn't working, is absolutely brilliant and you should go check it out. So in order to deal with those scales in physics, we use different prefixes, and these are the prefixes that you need to know. So femto times 10 to the minus 15, pico times 10 to the minus 12, nano times 10 to the minus 9, micro times 10 to the minus 6, milli times 10 to the minus 3, kilo times 10 to the positive 3, mega times 10 to the 6, giga times 10 to the 9, tera times 10 to the 12, and peta times 10 to the 15. You also need to know centi, which is times 10 to the minus 2, just like centimeters. And you'll see that these, like the big ones that are times 10 to the positive numbers, the vast majority of them are capitalized. The difference there is the kilo, which isn't capitalized. And then most of these little ones are regular letters, except for this micro here. That is a Greek letter, lowercase letter, mu, like what a cat would say, mu. It looks like almost like a Y backwards. So if I was going to draw that out, it would actually look like that, and the lines on the page would be here. It is a lowercase letter. So it's almost like a U that's got a tail off the start, but you draw the tail off the start first. So when we try to do conversions to the base unit, it's a pretty basic procedure. All you need to do to convert a prefixed unit to base units is multiply the value by the appropriate power of 10 given in that table. Now that table is also included as a handout on the Firefly page. You can print it off, but just be mindful that you don't need all of those prefixes. There's the +2, the +1, the -1, and then there's a few extra on the extremities that you don't need. So if you want to give it a try, pause the video and have a go. Example 1, convert 3 millivolts into volts. Well, the prefix milli corresponds to a standard form of 10 to the -3. So really all we do is, rather than writing that little m, we write times 10 to the -3 after that value, and the number is immediately converted into base units. So we've got 3 millivolts, or 3 instead of m times 10 to the -3 volts. It really is that simple. So the next example, pause the video and give it a try. So we've got 13.5 meganewtons into newtons, and mega means times 10 to the 6, so we would write this 13.5 times 10 to the 6 newtons. Now for those of you who are a bit stronger in math, you go, that just looks weird. 13.5 times 10 to the 6, why would you write it like that? And as a physicist, that's what we think as well. So while that number is completely correct, we're going to put it in a form that looks a lot better. And that's called standard form. If you haven't come across standard form before, it's a way of writing numbers in this format. So a number times 10 to the another number. And we always have that n as an integer. It can be a negative integer, but it's always an integer. That value of m can be any real number. However, we typically use normalized notation. So that 13.5 times 10 to the 6, that is a standard form. We've got 13.5 as our m and 6 as our n, but that's not normalized standard notation, which is why it looks a little bit funny. So in normalized notation, the real number must be between 1 and 10. So while 13.5 times 10 to the 6 is numerically correct, we wouldn't consider it normalized standard form. In order to get it into normalized standard form, we need to move that decimal place so that rather than 13.5, we've got 1.35. Whoops, not 10 to the 6. And that just means moving the decimal over that position. Now, some people get confused as to what number goes up here, and most of us go, right, we've moved the decimal one position, so this needs to change by one number. But does this mean it's a 5 or a 7? And the easiest thing to do is think about, you don't actually have to do it, but think about writing this number out as a big number, and if you've moved that decimal place, would that increase or decrease the number? And in this case, this would be times 10 to the 7. It can get a little bit awkward when you're dealing with negative exponents. So if we take, 53.9 times 10 to the -3, and we want to move that over, so it's 5.39 times 10 to the something, and people go, ooh, is that -2 or -4? Just think about writing it out. So we've got 0.0539, and that would be, 1, 2, 3. That would be our times 10 to the -3 there. And if we want to put our decimal here instead, that's 1, 2. So this is 5.39 times 10 to the -2. So if your exam specifies standard form, make sure you express it in the normalized variant. So this 1.35 times 10 to the 7, or this 5.39 times 10 to the -2. So to give you a bit of practice, the 6 questions below, you can convert each value into the base unit using the prefix adjustment, and then convert it into normalized standard form. I would always recommend that you do this in 2 separate steps so that you don't get yourself confused and you don't mess up on if it's a +1 or a -1 to the power of the 10. So pause the video and give question 1 a try, and then I'll show the answer. And then give question 2 a try, I'll show the answer, and so on and so forth. Pause the video now. So there's the answer to question number 1. Pause the video and try 2. There's the answer to question 2. Note that it's already in normalized form, so we don't need to do anything to it. Give number 3 a try. So there's our answer to question number 3. Be careful with that power in which way it goes. And there's our answer to question number 4. Pause the video, give number 5 a try. There's the answer to question number 5. Pause the video and give the last one a try. And there's the answer to question number 6. Notice that question number 6, that power actually got more negative, so -12 to -13, and that's because we needed to move the decimal over to a more negative place, which is a little bit different than the other examples above. So on the Firefly page, there's also a worksheet about trying to convert prefixes into base units, into different prefixes, and it's challenging, but it would be very good practice for you. And the answer sheet is up on Firefly as well. So you've got 2 tasks there to keep you entertained. If you need more, let me know, and I'll start teaching you dimensional analysis, which is just really cool with units. It's where you actually make up equations with your units, and astronomers do it loads, and it ends up giving pretty reasonable values. But if you do have any questions or want any sort of extension on that, just send me an email and let me know. Have a fantastic day.